Okay, so imagine a place deep in the ocean where sunlight literally never reaches. Ever.
Right. We're talking crushing pressure, near freezing water, pitch black.
You'd think nothing could live there, right? Just barren wasteland.
That's what most people thought, yeah. But scientists found these, well, they call them dense oases of life. It's pretty incredible.
Dense oases. Okay, so that brings us to the big discovery back in 1977 near the Galapagos.
Exactly. Hydrothermal vents. It just fundamentally changed our whole understanding of where life, where it could exist on Earth.
They found actual communities,
Oh,
like
yeah.
complex life.
Oh, yeah. Thriving communities. Giant tubeworms, loads of species nobody had ever seen before,
Hmm.
all living in complete darkness.
And they weren't using sunlight, obviously, so how?
That's the mind-blowing part. They're powered by Earth's chemical energy,
Yeah.
chemosynthesis. It was, well, completely alien compared to life up here.
Right. So with that amazing discovery as our starting point, today's deep dive is going to look into these really bizarre, unique deep sea ecosystems.
hmm We'll unpack how their food webs work, why they're important.
And crucially, the threats they're facing now, especially from deep sea mining, which seems to be ramping up.
Definitely. And to really bring that threat home, we'll be looking at how the IUCN, that's the International Union for Conservation of Nature, is applying its red list criteria down there.
The red list, like for endangered species on land?
Precisely. But applied to these extreme deep sea environments, we'll focus on hydrothermal vent molluscs. It's the first time they've done a full global assessment for these guys.
And I suspect the picture isn't pretty.
Let's just say you'll see just how precarious things are for a lot of these species. Very quickly.
Okay, so these hydrothermal vents, they're amazing, but also really rare, right? Globally speaking.
Extremely rare.
Yeah.
We're talking maybe 50 square kilometers of the seafloor total,
Yeah.
scattered around the globe. Tiny little hotspots,
50 square kilometers, that's it. Wow. But packed with life.
absolutely packed. And it all comes back to that process you mentioned, chemosynthesis. Instead of sunlight, you have microbes, bacteria, archaea, using
Wow.
chemicals from inside the earth.
Like hydrogen sulfide, stuff that smells like rotten eggs.
Exactly that. And methane, too.
Mhm.
They basically eat these chemicals, convert them into energy. They're the base of the food chain, just like plants on land.
So everything else depends on these microbes.
Everything. You've got grazers like limpets and shrimp munching on the microbial mats. You've even got yeti crabs that literally farm bacteria colonies on their hairy claws.
They farm bacteria. Okay, that's wild.
It really is. And then you have, the next level up. Secondary consumers like crabs, eels, octopuses, all adapted to these really hot chemical-heavy waters.
It sounds so isolated, though, like little lost worlds.
They seem that way, but they're actually surprisingly connected to the wider ocean.
How so?
Well, the larvae of many vent species can drift on ocean currents for, quite long distances. This creates these pathways, connecting different vent sites that might be hundreds of kilometers apart.
Ah, okay. So they're not quite as cut off as they seem. That's important.
It's critical, yeah.
So this dependence on a very specific chemical food source,
Mm.
does that make them tough because they're adapted to extremes? Or does it make them really fragile if things change?
Both, actually. It's a good question. They are incredibly specialized, very robust within that specific environment.
Right.
But because it's so specific, if you disrupt that chemical base or you block those larval pathways, well, the impact can be catastrophic.
Like fragile islands. If the island changes, the unique life there is stuck.
That's a great analogy. Highly adapted, yes, but highly dependent on that specific island staying the way it is.
And the connections go beyond just the larvae spreading out, don't they? I read about visitors.
Yeah, that's another layer.
Yeah.
You get animals like hagfish or deep-sea skates. They don't live at the vents full time, but they swing by.
To feed or lay eggs.
Exactly. They come in, use the resources, then leave again.
Mhm.
And then there are even pelagic wanderers.
Okay, what are those?
Think things like the Humboldt squid.
Yeah.
They might not even visit the vent itself, but they feed on the visitors who were just there.
Ah, so the energy from the vent gets carried even further out into the open ocean.
Precisely. It shows the influence of these vents stretches way beyond their immediate location.
And these deep sea plumes you mentioned earlier, the stuff rising from the vents?
Oh, absolutely vital. They spread out over huge distances. They're like highways for the larvae, like we said, but they also carry nutrients far and wide.
So they're seeding the wider ocean.
In a way, yes, exporting nutrients,
Yeah.
even affecting productivity much higher up in the water column. These plumes, they're not just local, they're part of global cycles. Think iron, sulfur, elements critical for life everywhere. even at the surface.
Wow. So these tiny hidden spots have a pretty big global footprint.
They really do, which makes the threats they face even more concerning.
Right. Let's talk about those threats. Deep sea mining is the main one you highlighted. What's driving that?
Well, it's the demand for metals. Industrially important metals, copper, nickel, cobalt, rare earth elements.
The kind of stuff we need for batteries, electronics.
Exactly. And these metals are found concentrated in certain deep-sea formations. Polymetallic sulfides, which make up those vent chimneys, or manganese nodules, which look like potato-sized rocks scattered on the abyssal plains.
And these formations are often right where these unique ecosystems are.
Yeah, very often, yes. Especially the sulfide deposits at hydrothermal vents. The problem is, well, getting those metals means destroying the habitat.
You basically have to remove the structures the animals live on.
You do. You destroy the creatures living directly on them, and you severely impact anything living nearby. And remember what we said about endemic species.
Species found only in that one specific location.
Right. So if you mine out a vent field, you could literally wipe out entire species that exist nowhere else on Earth.
Yeah.
Gone forever.
And the damage wouldn't necessarily stop at the site being mined, would it? Because of those connections.
That's the fear. Research suggests impacts could spread hundreds of kilometers away, affecting other vent sites through those larval pathways we discussed.
So mining one spot could doom others.
It could. And even mining inactive or extinct vents, which are often targeted for their minerals, isn't risk-free. It can stir things up, destroy habitats, potentially even reactivate venting unpredictably, or change water flows and heat at nearby active vents.
And what about the process itself? The digging, the machinery?
Well, that creates mining plumes, clouds of sediment and crushed rock in the water.
Like underwater dust storms.
Sort of, yeah, and they can spread really far. Modeling suggests maybe up to 70 kilometers.
70 kilometers, wow, and that smothers things.
It can smother filter-feeding animals, clog their gills, and potentially release toxins trapped in the rocks. Plus, think about those larvae drifting in the water column.
They'd be right in the path of these plumes.
Exactly. Plumes, noise pollution from the operations. It could devastate organisms during their most vulnerable life stage. Which brings us back to that IUCN Red List assessment. It's trying to quantify this risk.
Okay, so let's dive into those numbers. The Vent Red List for mollusks. What did it find?
It's pretty stark. They assessed 184 mollusk species that are endemic, only found at vents, and an astonishing 62% of them are listed as threatened with extinction due to potential deep-sea mining impacts.
62%. That's huge. How does that break down?
Well, you've got 39 species classed as critically endangered, 32 as endangered, and 43 as vulnerable.
So that's 114 species facing a serious risk of extinction.
Correct. Another 45 are near threatened. Only a tiny fraction, about 13–14%, are currently considered least concern.
And what's special about those least concerned species?
That's the really interesting part. There are almost all species found within areas that already have some form of protection, like marine protected areas or MPAs.
Ah, so protection actually works?
The data strongly suggests it does. There's a clear correlation. For instance, look at vent fields in the Indian Ocean, where mining exploration licenses have been granted by the International Seabed Authority. Those areas show the maximum possible threat score in the assessment. 100% of the mollusk species there are listed in threatened categories. 60% are critically endangered, many only known from that single licensed location.
Wow. So the license itself basically flags them as highly threatened.
Effectively, yes, under this assessment framework. Now, contrast that with, say, the East Scotia Ridge near Antarctica.
Okay, what's different there?
It's protected under the Antarctic Treaty System and also falls within a large marine protected area established around South Georgia and the South Sandwich Islands.
And the species there?
All 4 vent mollusks assessed there are listed as least concern. It's a night and day difference. It really illustrates how conservation measures, like MPAs or moratoria on mining, can directly reduce the extinction risk.
That's encouraging, that MPAs can work. But the deep sea is vast, these vents are scattered. Setting up enough MPAs sounds like a massive challenge.
Oh, it absolutely is a huge challenge. Just finding all the vent sites is hard enough, especially the inactive ones that might still be targeted for minerals but aren't actively, spewing chemicals.
Right, so mapping is step one.
Mapping is crucial. Then you need the political will, international cooperation. Because many of these areas are in international waters beyond any single country's jurisdiction.
The high seas.
Exactly.
Yeah.
And even when you establish an MPA, designing it effectively is complex. You need to understand those larval dispersal patterns to make sure the protected area is large enough that buffer zones are adequate.
Especially considering those sediment plumes traveling 70 kilometers.
Precisely. You need generous buffer zones. It's not simple. It's a really complex ecological and political puzzle.
Which raises the big why. Why should we, people listening, care so much about these tiny deep-sea snails and clams in faraway vents?
Well, beyond the basic idea of protecting biodiversity, these habitats provide tangible benefits, what scientists call ecosystem services. Well, think about potential resources, not just minerals, but biological resources. There was an enzyme, fuelzyme LF, discovered in microbes from these extreme vents.
Okay.
It turned out to be incredibly useful for industrial processes, like making ethanol biofuel more efficiently. It works at high temperatures where other enzymes would break down.
Ah, so they're like a natural bioresource lab down there.
Exactly, holding keys to biotechnology, maybe medicines that we've barely even begun to explore. They also provide critical habitat, obviously, and play that role in global nutrient cycling we talked about.
And there's a cultural aspect too, right? Like inspiring the search for life elsewhere.
Absolutely. Finding life thriving in such an extreme, non-sunlight-based environment on Earth really broadened our ideas about where life might exist on other planets or moons, places like Europa or Enceladus.
So they have scientific, potentially economic, and even inspirational value. They're actually designated as vulnerable marine ecosystems, aren't they?
Yes, under international frameworks, they are recognized for their unique vulnerability and importance.
Okay, so wrapping this up then, we have these incredible, unique, globally rare ecosystems powered by chemistry, deeply interconnected despite seeming isolated, full of unique life.
Life that provides ecosystem services, potential biotech solutions, and fundamental insights into life itself.
And yet, they are facing significant immediate threats from activities like deep-sea mining, putting a majority of their endemic species, like those molluscs, at high risk of extinction.
A risk that conservation measures like MPAs seem able to reduce, but implementing those effectively on a global scale is a major hurdle.
So maybe the final thought to leave everyone with is, what does this situation, this push to mine the deep sea, despite knowing so little and risking so much, what does it really tell us about our relationship with, well, the last true wilderness on Earth?
Yeah, especially when the potential impact seems so long-term, possibly irreversible, affecting not just biodiversity, but maybe even those global elemental cycles we rely on.
It really forces us to ask some profound ethical and very practical questions about how we proceed, doesn't it?
It certainly does. There's a lot to grapple with there.